Professor Dave and Chegg here. We've learned about sp3 and sp2 hybrid orbitals and the geometry that these centers adopt because of these orbitals. Let's finish things off by looking at sp orbitals and the types of molecules that utilize them.
We saw that a carbon surrounded by 4 electron domains will be sp3 hybridized, and if surrounded by 3 electron domains, it will be sp2 hybridized. Now we examine the situation where a carbon atom is surrounded by only 2 electron domains. When there are 2 electron domains, the atom needs to hybridize only 2 atomic orbitals, so it will be sp hybridized. This would be the case with something like carbon dioxide, as the 2 oxygen atoms are the 2 electron domains surrounding the carbon atom. Atoms that are sp hybridized exhibit 180-degree bond angles and linear geometry. That's why triple bonds between carbon atoms will be drawn like this when using line notation. Make sure to note that these are carbon atoms here, where the triple bond begins and ends, and the bonds that project immediately outwards from these carbons will continue in the same trajectory, giving us 4 carbons lined up in a row. This is due to the linear geometry that sp hybridization demands. To better understand this hybridization, let's look at acetylene, or C2H2, which has a triple bond between the carbons. This means the carbons are sp hybridized, exhibiting linear geometry. It is the case that the carbons need only one p orbital to generate the sp hybrid orbitals, so they each have 2 p orbitals left unhybridized. Therefore, we get 1 sigma bond between the carbons due to direct overlap of the hybrid orbitals, 1 pi bond due to lateral overlap of these p orbitals, and then another pi bond due to lateral overlap of these other p orbitals, which results in this propeller-looking configuration. The 2 hydrogen atoms will form sigma bonds via the 2 remaining sp hybrid orbitals. Again, rotation will be restricted due to the pi bonds, as disruption of the lateral overlap would disrupt the pi bonds, and any triple bond will necessarily involve 1 sigma bond and 2 pi bonds, as shown here. As we might expect, triple bonds are even shorter and stronger than double bonds, which, as we already learned, are shorter and stronger than single bonds.
With sp orbitals and the geometry of acetylene now understood, we have a better understanding of different types of hybrid orbitals, as well as the differences between sigma bonds and pi bonds. Professor Dave for Chegg. See you next time.